I can start. Huh? Okay. Okay, my dear student friends. Again, thank the organizers for their good work, particularly in providing 8 online classes for all the interest students across the state. Yesterday, we have completed fluid statics also. I mean, fluid properties of fluids, fluid statics, hydrostatic forces, and fluid kinematics. So, one important question. I'm happy really, my student friend. He has asked me, or rather, he has mailed me one important question. The question is in the chapter. So I'm not. I'm telling the question orally. I'm not taking up the other chapter. So the question is on surfaces. So the problem is he has asked to find out the distance between center of gravity and center of pressure. Center of gravity and center of pressure coincides each other for horizontal plane surface. For vertical plane surface, center of pressure lies below center of gravity. That I think you know. The question is, he has taken a circle and from the top, the depth of immersion is doubled. The depth of immersion of a circular vertical plane surface is doubled. What is the change in the distance between center of gravity and center of pressure? Wonderful question. Let us say this is the vertical plane surface. We have a CG distance x bar here. So this is, let us say, he has given a circular surface, vertical circular surface. The question is asking the distance between the center of pressure and center of gravity when the depth of immersion is doubled. So this is the surface here, same surface, same area, same moment of inertia also, because this is the vertical plane surface, and now it is doubled. Depth of immersion means from here, let us say x bar. So this is now it is doubled. Then what happens to the distance between CG and CP? That was the question. Double or half or equal, something like that. And on that day, it is definitely a gap. So I told there will not be any change in the distance. But after thinking, because the question raised by the student, I thought I am working on that. I also taken the opinion of experts. So the distance between center of gravity and center of pressure, as you know, distance between center of gravity and center of pressure is ICG, moment of inertia of CG by AX bar. ICG, moment of inertia about CG by AX bar. The center of gravity, distance between center of gravity and center of pressure, which is in other words H is equal to x bar, h bar is equal to x bar, and from here to here, this is ICG, moment of inertia about CG by A x bar. So even the depth of invention is doubled, the moment of inertia is same. Moment of inertia because ICG is pi d 4 by 64. For the circle, the center of gravity of moment of inertia about center of gravity is pi d 4 by 64. Even if it is doubled, depth of inertia is doubled, there is no change in moment of inertia. ICG by x bar, the area. So the area of the circle is same. So because it has not changed the area, so ICG A both are same. So the distance between CG and CP is equal to ICG by x bar. So ICG and A both are constant for both the cases. So it depends on 1 by x bar. So distance between CG and CP, ICG by x bar, ICG and A are constant. So it is proportional to 1 by x bar. The distance between CG and CP is proportional to 1 by x bar. So now the depth of invention is doubled. So this is proportional to 1 by x bar. And suppose if you take the 2 times of that, the center of gravity must be equal to 2 times of x bar for the new case. So x bar is, if the depth of invention is normal, now it is doubled. So the center of gravity further case is x bar. If it is doubled, if it is coming down, provided other properties everything is same, so the x bar is equal to 2 times x bar. So earlier case it is proportional to x bar. Now the case it is in place of x bar, as it is doubled, it is 2x bar. So in other words, the center of gravity to center of pressure distance, if the depth of invention is doubled, the answer is 1 by 2, half. Thank you very much, student friend. So that it is a very good question and requires answer for all the students. I thought it should be mentioned here in the class itself. Thank you, my student friend. And finally, the answer is 1 by 2. Not coincidence that it is 1 by 2. So because the distance between center of gravity and center of pressure is ICG by x bar, ICG A are constant, and it is proportional to 1 by x bar. If the depth of immersion is doubled, provided everything is same, the CG also doubled to x bar. So it is proportional to 1 by 2x bar. In other words, the difference is only half. So distance between CG and CP will be half if it is if the depth of invention is doubled. So come back to the normal fluid dynamics now. Fluid dynamics, as I already told you, in this chapter we are concentrating on forces which are responsible for the fluid motion. What are the forces which are responsible for the fluid motion? Fluid dynamics, we have a body force, surface force and volume force. Body force, surface force and volume force. We have body force here. So body force is proportional to volume force. Example, weight, centrifugal force. Body force or volume force, it is also called volume force. It is proportional to volume. Name itself is volume force. Body, entire body, proportional to volume. So the volume is, example of volume is the weight. So weight depends on volume, or mass depends on volume. So the examples for body force are weight or mass. Again, surface force. Surface force is proportional to area. Surface force is proportional to area. So any force proportional to area is example for surface force. So you can take shear force. Shear force is equal to shear stress into area. So shear force is proportional to A square. So the example for surface force is shear force. Again, pressure force. Pressure force is equal to pressure intensity multiplied by area, surface area. So pressure force is equal to intestinal pressure multiplied by area. So the surface force examples, you can take pressure force and also shear force. And the third one, line force. Line force. So the line force, the name is very clear, body force, surface force, line force. So line force is proportional to length. Line force is proportional to length. So what are the examples for line force? What are the examples for line force? If you remember the definition of surface tension, so surface tension is the force required to maintain the unit length of film in equilibrium. Surface tension is the force required to maintain unit length of film in equilibrium. So the unit of surface tension is Newton per meter or kg per meter. So line force is, if we take surface tension force, which is equal to surface tension multiplied by length. So the line force example is surface tension. Line force example is surface tension. And in this chapter, what are the different forces normally you consider? What are the different forces normally you consider for the study under dynamics? The forces are due to gravity, force due to gravity. Obviously, there is a force due to gravity, whether it is a fluid, statics, or dynamics, whatever it is. Without gravity, gravity is the weight. So, force due to gravity means because of the weight of the fluid, which is acting downwards, you can expect a gravity force. The other one is pressure force. So, the pressure force on one face and the pressure force on the other face, which is a distance of L, when a fluid is moving, the pressure changes from point to point. Pressure force is because, let us say, when the fluid is moving on account of shear stress. So, on one particular point, the pressure is P, and suppose if you go on moving in the flow direction, the pressure force at the other location is entirely different. So, you can expect a pressure force because of the change of pressure between 2 points in a flowing fluid. So, the pressure force is due to the pressure change between any 2 points in a fluid. The other one is viscosity. Viscosity, enough known. Viscosity is the property of the fluid by virtue of which fluid offers resistance to deformation. It is very clear, viscosity. Then the viscosity, because of the real property, because of the practical nature of the fluid, the viscosity for the real fluid, for the practical fluid, the viscosity is compulsory. The viscosity property need to consider for practical fluid. So in view of the real fluid, the viscosity force is required to be considered when the fluid is set in motion under the application of shear stress. Resistance is offered in the opposite direction. So that is viscosity. So we have because of the real property, due to viscosity of the flow, you can also have a viscous force. The other one is turbulence. So we have a laminar flow and a turbulent flow. So laminar flow is the flow in which the flow is steady, stable, regular, and there is no intermixing, and flow steadily. You can expect that in a small diameter tube when it is moving at a low velocity, that type of flow. Not necessarily the forces for laminar flow, but turbulent flow, turbulence, force due to turbulence. So turbulent flow, as you know, when the fluid particles are moving, the movement is irregular, the movement is erratic, and there is a formation of eddies at some place when you consider turbulent flow, erratic flow, irregular flow, and intermingling of fluid particles from top to bottom and bottom to top, everything, whatnot, everything. So because of the formation of eddies, because of turbulence, you can also expect the force due to turbulence of fluid, due to turbulence of fluid. Then we have due to force due to compressibility. What is compressibility? So compressibility, as you know, it is a measure of change of volume with the application of pressure. When the pressure is applied, what is the change in volume? Is compressibility inverse of bulk modulus, and K is equal to change of pressure dV by V. dV is equal to, K is equal to dP by V. Change of pressure, with increase in pressure there is decrease in volume, compressibility. So when pressure is applied, there is a compressibility in the fluid. So due to elastic property of the flow, so compressibility behavior, due to elastic property of the flow, you can always expect that there is a force can be caused due to compressibility behavior of the fluid. The other one is surface tension. Force due to surface tension. Earlier discussion, if you remember, the force surface tension is due to cohesion, and capillarity is due to both cohesion and adhesion. Surface tension is due to cohesion, and capillarity is due to both cohesion and adhesion. So you can also expect a surface tension force due to cohesive property of the fluid. As there is a cohesion, as there is intermolecular attraction for the fluid, you can also expect surface tension. And we have three important equations: Euler's equation of motion, Navier-Stokes equation, and Reynolds equation of motion. Euler's equation of motion, Navier-Stokes equation, and Reynolds equation of motion. So Euler's equation of motion is important, which is included in the syllabus. If the force due to gravity and force due to pressure are considered, only, and neglect all other forces, consider we have 6 forces here. One is gravity, pressure force, viscosity, turbulence, compressibility, and surface tension. So if you neglect the force due to surface tension, due to compressibility, due to turbulence, and due to viscosity, if you neglect all the other forces, if you consider only gravity force and the pressure force, the resulting equation is Euler's equation of motion. Similarly, Navier-Stokes equation. So Navier-Stokes equation, so when you consider inertia to gravity and pressure, if you consider force due to viscosity, you can say that it is Navier-Stokes equation. So that means we have neglected all the other forces: turbulent force neglected, compressibility force neglected, surface tension force is neglected. We have taken only gravity force, pressure force, and force due to viscosity. So here, this is the gravity force, pressure force, and force due to viscosity. We consider only those forces, and if you arrive an equation, so that is called Navier-Stokes equation. The last equation is, this is important for object drive. That's why I am stressing this. We have object equations on these equations here. Reynolds equation of motion. Suppose if you neglect force due to compressibility, force due to surface tension, then the resulting equation is Reynolds equation of motion. So Reynolds equation of motion is gravity force, pressure force, force due to viscosity, force due to turbulence. So if you neglect surface tension and compressibility and consider gravity force, pressure force, force due to viscosity, and turbulence, then you can say that it is Reynolds equation of motion. These are the three equations. You need to remember which forces if you consider for arriving at Euler's equation of motion, and which forces can you consider for arriving in Navier-Stokes equation, which forces can you consider for arriving Reynolds equation of motion. We have Euler's equation. So very important, Bernoulli's equation, Bernoulli's equation. So if you do integration of Euler's equation, so that means in the Bernoulli's equation we will be considering only gravity force and pressure force. We will be considering only gravity force and pressure force. And if you consider only gravity and pressure force and the resulting equation, if it is integrated, the equation is called Bernoulli's equation. Very important questions are there on Bernoulli's equation. So Bernoulli's equation we will consider only gravity and pressure force, and the resulting equation is Euler's equation, and integral of Euler's equation is Bernoulli's equation. Some important steps which are necessary for solving gate problems also while deriving the Bernoulli's equation. So there is only one procedure which you can get Bernoulli's equation is when you consider the flow along the streamline. Derive Bernoulli's equation along the streamline for study encompassed by rotational flow. It is a common question in any examinations. You may ask derivations, but how one can find out the pressure force, how one can find out gravity force, all these things. Indirectly, you may ask some questions in the derivation part of this Bernoulli's equation. I am not trying to do the derivation of Bernoulli's equation, but what are the important aspects and concepts based on that one can derive Bernoulli's equation. Suppose if you see here, this is a stream tube or streamline. So before starting the derivation, one should know what exactly mean by streamline. Streamline is a line drawn to the flow field, a series of streamlines, and take a point on the streamline. If you draw a tangent, that gives direction of velocity. And the streamlines which give directions of velocity of different fluid particles at a particular time. And as it is giving any point on the streamline, if you draw a tangent, as it is giving the direction of velocity, we cannot resolve the tangent in the normal direction. You cannot resolve that in the 90 degrees. So there is no normal component to the velocity vector, which is the direction of the velocity when you draw a tangent to a particular point. Then you can say that there is no flow across a streamline, no flow across a streamline. The flow is only in the tangential direction. If you take a streamline, the derivation of streamline, you are simplifying the derivation on one-dimensional case. You can as well only consider one-dimensional case, that is tangential direction. So now what are the forces here? We need to consider only two forces here, pressure force and body force. So body force is weight force, force due to weight. Pressure force. So let us come one by one. What is the procedure for finding out pressure force? Earlier we have discussed some procedure for finding out the pressure. Examples also. In derivation of continuity equation also I have given how we are going to find out the pressure, unknown pressure at different points when the pressure at one point is known. Now let us say the intensity of the pressure here is small p. Intensity of the pressure is small p, which is equal to force by area. So the area of the cross section is dA. So the pressure intensity is P and the area is dA. So then what is the force here? P into dA. Pressure force at this location is P into dA. Then what is meant by net pressure force? So we have pressure force here, and it is required to find out the pressure force at the end of streamline here. So we are considering this as a steam tube, and we have considered this is one location. and this is other location. So find out the pressure force here. So the pressure force at the other section. So here the pressure force is P into dA, pressure intensity to area. Then find out the pressure intensity here. The area is same, area is dA, and the length of this is ds here. So from here you are moving towards positive x-axis. So the sign is also important. Whether you take positive or negative, that is also important. So while you are moving in the positive direction, you can take positive sign P plus. And what is the change of pressure in the s direction? So it is not x, y or z. So it is the tangential direction. So the change of pressure in the s direction, that is dp by ds, and the distance from here to here is ds. So that you can cancel these two, and the final, this is the change in pressure. When you move from this point to this point, the change in pressure is dp by ds into ds. So the pressure intensity here is equal to P plus dP by ds into dA. So this is the pressure intensity multiplied by area. So that is the pressure force here. This acts towards the negative x-axis. This is acting in this direction. This is acting in this direction. So find out the net pressure force. So net pressure force is equal to P dA minus P plus dP by ds into dA. So pressure force, net pressure force, FPS is the net pressure force, which is equal to P dA minus of P plus dP by ds into dA, which is equal to minus, if you take negative sign as is, so this is equal to minus dP by ds into ds dA. So ds dA is volume here, and dP by ds is change of pressure in the direction. So FPS, net pressure force in the tangential direction, which is equal to minus dP by ds into ds dA. And actually, as you know, this is F is equal to ma. Force is equal to mass into acceleration. Force is equal to mass into acceleration. It is Newton's law of motion. So the forces you consider, one is the gravity force here. If you want to arrive an equation, Euler's equation, then you need to consider gravity force and pressure force. This is the pressure force you have considered here. Mass into acceleration is equal to F. F is sum of forces here, and this is the pressure force. And the other one is, this is the gravity force. So FGS just represents the force in the tangential direction. As you know, the weight acts always in the vertical direction. Weight acts always in the vertical direction. Then it is required to resolve this weight in the direction of tangential direction. You know, by knowing the angle theta here. By knowing angle theta, we can resolve the weight. So the weight, as you know, from the center, it is always acting downwards, and find out the angle between the weight and the theta, which is required for resolving into the direction of tangential direction. And what is the weight here? So weight is equal to specific weight into volume. Specific weight is weight by volume, and weight is equal to specific weight into volume. So the volume here is, so ds is the length and dA is the area. So area into length is the volume. So ds is the volume, and the weight is equal to the specific weight multiplied by the volume. So this is specific weight. This is small w here. So the gravity force is specific weight into dA ds. This is specific weight and dA ds, and the angle in which it is resolved is cos theta. So you can find out pressure force in the x direction and gravity force in the s direction, and resulting are, we have acceleration as and also mass. So the mass is equal to, you know, mass density is mass by volume. Mass density is mass by volume. So mass is equal to mass density into volume. So this m, we can take mass density is the rho into dA ds. dA ds the volume. So m is known here, FGS is known here, FPS is known, and now it is as. As is the tangential acceleration, So earlier I have discussed with you regarding tangential acceleration. If as you know, Vs is the tangential velocity, which is equal to distance moved in the s direction by time as dt tends to 0. So Vs is equal to limit dt tends to 0 ds by dt, and As, acceleration in the tangential direction, is dBs by dt, change of velocity in the tangential direction by time as time tends to 0. In the general form, we can write that Vs dVs by ds and dVs by dt, and Vn can be neglected as there is no normal flow, normal velocity. You can straight away take Vs dVs by ds plus dVs by dt. Actually, we have Vn component also, but that can be neglected as there is no existence of Vn for the streamline, because you cannot get any normal component, so the velocity Vn is 0. That's why there is no second term here, Vn. And we have Vs into dVs by ds plus dVs by dt. So what is dVs by dt? So this is change of velocity with time, and this is change of velocity with distance. Change of velocity with time, this is change of velocity with distance. Then, if we assume the first assumption here, if we assume the fluid as steady, steady means any property with reference to time. If all the properties with reference to time, when they are constant with reference to time, we can say it is a steady flow. Steady flow is the flow for which all the properties are constant with reference to time. So the velocity with reference to time, if you assume the fluid as steady, the dVs by dt is equal to 0. So now we have the value of m here and As here. As is Vs dVs by ds, this is 0, and Fgs here appears here. Use all these equations and you can get the equation here. So the resulting equation is Euler's equation, and you can do integration. So integration of the equation, that gives the Bernoulli's equation. So you can define that for the ideal fluid, for steady irrotational of an incompressible fluid, we have also assumed the fluid as incompressible. Incompressible means mass density is constant. So if you see this equation, there is no mass density here. So we have also assumed the fluid as incompressible, irrotational and steady. So the total energy at any point is constant. In other words, total head is constant in a flowing fluid for steady, irrotational and incompressible fluid. For steady, irrotational and incompressible fluid, the total energy at any point is constant. So the total head, what is meant by total head? At point 1, total head at point 2. So total head at point 1, so the total head is sum of, this is the pressure head here, as you know. So the pressure head at point 1 is P1 by W, and this is the velocity head. P1 square by 2G is the velocity head, and this is the datum head. The total energy of the total head is the sum of pressure head. Important object type. One object type is state Bernoulli's theorem, and you will confuse ABCD. So for steady rotational flow of an incompressible fluid, total energy at any point is constant. And the second one is total head. So the total head is the pressure head here, the P1 by W, as you know from the fundamentals of pressure chapter. This is the pressure head. And V1 square by 2G is a velocity head. V1 square by 2G is velocity head, and Z1 is datum head. V1 square by 2G, velocity head. So that means you need to have the values of P1 and V1 at section 1. P1 is pressure and V1 is velocity head or dynamic head, and Z is datum head. So they mean sea level and Bombay, normally considered as datum. Datum head is with reference to a known elevation. What is the height of the point 1? With reference to known elevation, the elevation is known with reference to that. With reference to that, what is the height of the point 1? So that is Z1, which is equal. This is the total head here. This is the total head here. And this is P2 by W plus V2 square by 2G plus Z2. P2 by W plus V2 square by 2G plus Z2. So once again, this is pressure head, velocity head and datum head, pressure head, velocity head and datum head. The pressure head at point 2 is Pt by W, the pressure at point 2 is P2, the same fluid is flowing, that's why I have taken same W. V2 square by 2G, V2 is the velocity at section 2 and Z2 is the datum for the section 2. The fluid may not be horizontal, the pipe may not be horizontal, the pipe may be inclined, the pipe may be some other direction. So Z1 may not be equal to Z2 if it is not horizontal. The pipe is horizontal, you can take Z1 is equal to Z2, the datum. Both datums are same with reference to a standard datum. And Z2 is the datum head with reference to location 2 or point 2 with reference to some known datum. This equation is for ideal fluid because we have not considered losses here. We have not considered losses here, so this is ideal fluid. And the other one is real fluid. Real fluid, as you know, is a practical fluid. You need to consider the losses. You need to consider losses. So it is P1 by W plus V1 square by 2Z plus Z1 is equal to Pt by W plus V2 square by 2Z plus Z2 plus HL. So what is HL? HL is the loss of head. HL is the loss of head between points 1 and 2 when there is a flow from 1 to 2. Because the real fluid you can expect a viscosity, and when the fluid is flowing from point 1 to 2 you can expect a opposite force which is acting in the flowing fluid, that is due to viscosity. This is the loss of head here. Loss of head when the flow is from A to B, a flow is from 1 to 2. If the flow is from 2 to 1, you need to consider HL in this direction here. So this HL I have considered here by assuming that the flow is from 1 to 2. The flow direction depends on this value. So if P1 by W, V1 square by 2G plus Z1, if it is more than Pt by W plus V2 square by 2G plus Z2, then you can say that the flow is from 1 to 2. To make a same total head here, you can consider losses here. HL is the loss of head due to losses. We can always consider another point when the flow is from 1 to 2. When the flow is from 2 to 1, let us say when the flow is from 2 to 1, so this HL you need to consider here. So this is a Bernoulli's equation and which is very much required. One is a continuity equation which is du by dx plus dv by dy plus dw by dz is equal to 0. The other one is discharge equation, q is equal to a1 b1 is equal to a2 b2 is equal to a3 b3, and this is the Bernoulli's equation. So the combination of Bernoulli's and continuity equation we can solve many fluid problems. The concept of Bernoulli's equation, continuity equation, almost the fluid mechanics depends on the application of continuity equation, Bernoulli's equations. We have momentum equation also, I'll come to that. But these two are the important equations, and almost these two equations are dominating the fluid mechanics, particularly in solving fluid flow problems. So real fluid, this is HL, loss of head, and suppose if you see here, sometimes he may give a piezometric head. He may ask you piezometric head. So piezometric head is P1 by W plus Z1. Suppose summation of pressure head and datum head, summation of pressure head and datum head is piezometric head. So P1 by W plus Z1, the pressure head and datum head is also called piezometric head. And here piezometric head is Pt by W plus Z2. So the piezometric head is P by W plus Z. For this case, P1 by W plus Z1 is the piezometric head at section 1. And P2 by W plus Z2 is piezometric head at section 2. And take a small problem on that. The water is flowing through a pipe having the diameters 20 centimeters and 50 centimeters. x-axis 1 and 2 respectively. So diameter D1 is 20 centimeters, diameter D2 is 15 centimeters at section 1 and 2. Rate of flow through pipe is 14 to 10 power minus 3 meter cube per second discharge. Rate of flow through pipe is discharge. Section 1 having diameter 20 centimeters, section 2 having diameter 15 centimeters. And the discharge through pipe is 14 to 10 power minus 3 meter cube per second. Section 1, 6 meters above datum line. So the Z1, so Z1 is 6 meters and section 2 is 3 meters. So that is Z2. Z2 is 3 meters here. He has asked to find out the pressure at section 1 is 3 kg force per square centimeters. Find the intensity of the pressure at section 2. He has given the complete data. So now we use continuity equation. Use continuity equation. Q is equal to A1 V1 is equal to A2 V2. And we have a value of Q here. Q is 14 to 10 power minus 3 meter cube per second. And A1, D1 is known here. So D1 is known here. So A1 is equal to pi by 4 D1 square. So pi by 4 you can convert into meters. So pi by 4 into 0.2 whole square. And the velocity V1 you can find out. So V1 is equal to Q by A1. So V1 is equal to Q by A1 and which is equal to 1.27 meters per second. 1.27 meters per second. And V2 again we have the value of Q here. Q is equal to A2 V2. Q is equivalent to 14 to 10 power minus 3 meter cube per second and A2 is a pi by 4 0.15 square. You can find out V2 is equal to Q by A2, that is equal to 2.26 meters per second. 2.26 meters per second. And now the apply Bernoulli's equation P1 by W plus V1 square by 2G plus Z1 which is equal to PT by W plus V2 square by 2G plus Z2. So the value of P1 is 3 kg per centimeter square. So 3 kg per centimeter square is equal to 3 into 10 power 4. 3 into 10 power 4 kg force per meter square. So P1 is equal to 3 into 10 power 4 by the value of W is equal to 1000. Specific weight of the fluid in MK system 1000 kg force per meter cube. So 3 into 10 power 4 kg per meter square by 1000. V1 is 1.27. 1.27 square by 2 is 9.81. And what is Z1? So Z1 is the datum here. Section 1 is 6 meters above datum line. So Z1 is 6 meters here. And P2 is not known. And V2 is 2.26 here. So V2 is 2.26 square by 2 into 9.81. G is 9.81. Then Z2. So Z2 and section 2 is 3 meters above the datum. So Z2 is equal to 3 meters. Z2 is equal to 3 meters. So this is 3 meters. So you have all the values except P2 here. So P1 is 3 into 10 power 4 by 1000 and 1.27 square by 2 into 9.81 and Z1 is 6 meters here and P2 by W not known. V2 square by 2G 2.26 square by 2 into 9.81 and Z2 is 3 meters here. Everything is known here. So I can obtain P2 is equal to 3.28 kg force per square centimeters. More or less the gate problems in this chapter mostly depends on these equations. One is continuity equation, the other one is Bernoulli's equation. With the help of these two, so you can find out the discharge equation and the Bernoulli's equation you can find out unknown. The second problem. So this is the problem under real fluids. This is the problem under real fluids. P1 by W plus V1 square by 2G plus Z1 which is equal to P2 by W plus V2 square by 2G plus Z2 plus HL. So you need to find out the loss of head here. A pipe of diameter 30 centimeters, constant, carries water at a velocity of 20 centimeters per second. The pressures at section A and B. So we have two locations here, A and B. The water is flowing. A pipe, there are two locations in the pipeline in which fluid is flowing. We have A here, we have B here. So the pressures at section A and B, 3.5 and 3 kg per centimeter square. The data here is also given A and B, 25 meters and 28 meters. It is all given, but it has not mentioned the velocity at section 2. So one thing you can observe from here is the diameter is same. So when the diameter is same, if you have the discharge equation, Q is equal to A1 V1 is equal to A2 V2. When Q is equal to A1 V2, A1 V1 is equal to A2 V2. So when the diameter is same, A1 is equal to A2. When A1 is equal to A2, then V1 is equal to V2. So when the diameter is same, A1 is equal to A2. To make it equal, V1 is equal to V2. So as two are same, as V1 and V2 are same, so V1 square by 2G and V2 square by 2G can cancel, both are equal. Then the equation simplified to P1 by W plus Z1 is equal to P2 by W plus Z2 plus HL. HL is the loss of head between A and B. HL is the loss of head between A and B. So P1 by W plus V1 square by 2G plus Z1. So the velocities V1 square by 2G both are equal, as V1 is equal to V2. So can cancel V1 square by 2G and V2 square by 2G. And P1 by W and Z1 is equal to P2 by W plus Z2 plus HL. HL is the loss of head. It has also to find out. Then P1 by W. P1 by W is 3.5 into 10 power 4 kg per meter square by 1000. 3.5 into 10 power 4 by 1000. And Z1, so Z1 he has given at A is 25 meters here. And P2 he has given 3 kg force per square centimeters. So 3 into 10 power 4 by 1000. And the velocity 0. And Z2 is 28. Z2 is 28. So then P1 by W is equal to 3.5 into 10 power 4 by 1000. So this is 35. And Z1 is 25. So 35 plus 25, 60. 60 on this side. And P2 by W, P2 by W is 3 into 10 power 4 by 1000. So this is 30. And Z2 is 28. So P2 by W plus Z2, this is 0. So this is 58. So 60 is equal to 58 plus HL. 60 is equal to 58 plus HL. So HL is equal to 2. This is a very simple problem, but many number of students are doing mistakes. They are taking V1, V2. They are confusing with HL. Simple answer. The loss of head between 2 points A and B is 2 meters. And this discussion so far, which will be helpful for you, particularly in solving many gate related questions and problems. The other equation is Newton's equation of motion. Newton's equation of motion. I want to discuss a momentum equation. That's why the fundamental equation for finding out the force is Newton's equation of motion, mass into acceleration. What is mass here? Force acting on a fluid mass is force, and A is the acceleration acting in the same direction as that of force F here. Fundamentals, I am going to fundamentals. F is equal to ma. So in which F is the force acting on a fluid mass m, and what is A? A is the acceleration acting in the same direction as that of force applied. Then momentum equation. So you can take F is equal to MA, which is equal to d of dt by MV. In other words, that the mass here, the mass is m and acceleration is dv by dt. dv by dt is rate of change of velocity. M dv by dt, I have taken mass also inside. So this is modified form of Newton's equation. Momentum equation is modified form of Newton's equation. The acceleration is dv by dt, and as mass is m is constant, you can take inside. So this is equal to d of mv by dt is a momentum equation. Then what is m into v? M into v is momentum. So this is d of mv means change of momentum, that is final momentum and initial momentum by time. So the momentum equation defines that the rate of change of momentum in any direction gives the force in the same direction. The momentum equation defines that the rate of change of momentum is, rate means time. This is rate of change of momentum in any direction that gives the force in the same direction. So which is also equal to rho q. Rho means mass density and q is resource into v2 minus v1. The quantity is assumed constant and velocities are changed. So this is general form. More general form, we can write a momentum equation. F is equal to rho q, rho into q, v2 minus v1. So v2 is the velocity at 2 and v1 is the velocity at section 1. Rho is the mass density and q is the discharge. And this you can take in different directions. So fx, you can take fx here. Fx is equal to rho q, v2x minus v1x. Fy, rho q, v2y minus v1y. Fz, rho q, v2z minus v1z. You can take f in x direction, y direction and z direction. And the resultant f is equal to square root of fs square, fy square plus fz square. That is the momentum equation. Then what is impulse momentum equation? Suppose if you further change this momentum equation, f of dt is equal to d of mv. So I have taken this dt in this side. So this is f of dt which is equal to d of mv. F of dt is equal to d of mv. So f of dt is the impulse momentum equation. So impulse means the force acting in a short interval of time is called impulse. So impulse means the force acting in a short interval of time. So the force in a small interval of time dt. So that is called impulse. And momentum, this is change of momentum, not rate of change of momentum. Some students they are writing right here. So rate, I have taken dt in this sign. So this is only change of momentum. So change of momentum is equal to the force acting in a time dt. So the direction of force acting and also the fluid moving, which are in the same direction. So this is the application part. I will come to the application part of momentum equation. We'll have break. Now it is 11:30. We'll have a short break, maybe 5 to 7 minutes. Please refresh and take water. And again, we'll be back in maximum 5 minutes, 11:35. Okay, student friends, we are discussing impulse momentum equation. Momentum equation. Gaussian was also given momentum equation. So momentum equation is rate of change of momentum, which is equal to force. Rate of change of momentum is equal to force acting on the mass of the fluid m in the same direction. So take one practical example, forces on the bend. So we'll use momentum principle for solving the pipe bend issues. So this is the pipeline which is carrying fluid here. This is called bend pipe. So the pipe is not horizontal here, horizontal here, and from here there is a angle of bend is theta, and which moves, it starts here and moves in this direction. And which forces are really required to keep it in equilibrium? Or which forces are necessary to take up this issue? So we have three important forces. We have pressure force here. So this is section 1 and section 2. This is section 1 and this is section 2. So we have pressure forces here. Pressure force here is P1A1. Intensity of the pressure P1. The pressure intensity here is P1. The pressure intensity here is P2. And A1 is the cross section area. And A2 is the cross section area. So P1A1, the pressure force here, and P2A2 is the pressure force here. So one force is pressure force at section 1 and section 2. Then what are the other forces? The other forces are, we have weight of the fluid here, weight of the fluid acting downwards. The second force, which is required for consideration, is weight force here. So the weight is vertically acting downwards. Wherever it is weight acts vertical downwards. So one is the pressure force, second one is weight of the fluid, and the third one. So when the fluid is flowing through a pipe and the pipe sides are closed here, the fluid is moving, what happens here? So there will be obviously a force by the fluid on the bend. So when you resolve the force in the x direction, this F is the force by the fluid on the bend, Fx. So this force, the force in the vertical direction, this is the force in the x direction, this is the force in the y direction. So this is acting at an angle theta here. So the forces in the x and y directions is the force by the fluid on the bend. If you take a force by the bend on the fluid, it is equal to, say, it is equal magnitude but opposite direction. So F is equal to minus R, or R is equal to minus F. Let us say R is the force by the bend on the fluid. R is the reaction by the bend on the fluid. So that R is equal to minus F. Same in magnitude. The force by the fluid on the bend and also reaction, both are same, but opposite sign, opposite directions. So F is equal to minus R, or R is equal to minus F. But consider here the force by the fluid on the bend. So Fx is the force in the x direction, force in the y direction. It is required to find out Fx and Fy, the force by the fluid on the bend, and find out the resultant. So F is equal to square root of Fx square. F is equal to square root of Fx square plus Fy square. And now the forces are known here. We have pressure forces here, and force by the fluid on the bend, and weight. Then we have the equation, if you remember, Fx, F is equal to rho q, V2 minus V1, or Fx, Fx is equal to rho q, V2x minus V1x. So this Fx is sum of the forces in the x direction, which is equal to rho q V2x minus V1x, and Fy sum of the force in the y direction, which is equal to rho q V2y minus V1y. So then apply these two equations here. The application of moment equation we are discussing. Force exerted on a pipe bend. So take the forces here, the sum of forces in x direction. Sum of force in the x direction here, and this is sum of force in the y direction. So the sum of forces here in the x direction. So x direction, let us say this is the positive sign here. And when you consider the forces in the positive direction, you can take, this is the positive sign here, this is plus sign. So when you take the forces here in this direction, so upward direction is positive here, and here the direction towards the positive axis is the positive sign here. So take the sign convention like this. And suppose if you see here, this is P to A2. So this is P to A2. And the angle of the bend is theta. Angle of the bend is theta. Then resolve this in the horizontal direction. Resolve this in the horizontal direction. So this is P to A2 cos theta, which is acting in the negative x-axis direction. And this is P to A2, and this is theta here, and this is P to A2 sin theta. So P to A2 sin theta is acting vertical downwards here. And again velocity V2 here. So V1 is also acting in the same direction. V1 is also acting in the same direction. And this is V2, we can resolve into two directions here. So V2, when you resolve in two directions here, so this is V2 cos theta. So when you resolve in the vertical direction, this is V2 sin theta. So V2 cos theta and V2 sin theta. So V2 cos theta is acting in the positive x-axis, and V2 sin theta is acting in the upward direction. The weight always downward direction. So the importance here is not only resolution of forces, but you need to give the directions appropriately. You need to give the directions correctly, otherwise the problem will be wrong. So this is the direction here, this is the direction here, and this is the direction here, this is here, this is here. And take positive in the positive x-axis and negative in the negative x-axis, and positive in the upward direction and negative in the downward direction. Otherwise your entire exercise will go wrong. So now we take the sum of forces in x direction. So sum of force, first you consider pressure force here, P1A1, because it is moving towards this side, P1A1 is plus here. And we have P2A2 cos theta. So this is acting towards this side, and this is acting towards this side. So P1A1 minus P2A2 cos theta. So you see here P1A1 minus P2, so this is theta. P2A2 cos theta. And there is another force here, Fx. So Fx is also acting in the positive x-axis. So P1A1 minus P2A2 cos theta plus Fx. So these are the sum of the force in the x direction, which is equal to mass density into discharge into final velocity V2 in the x direction minus V1 in the x direction. So then find out the velocity in the x direction. So the velocity V1 in the x direction is V1. The velocity V2 in the x direction here, if you see here, this is acting this positive x-axis. This is equal to V2 cos theta. So rho q is rho q into V2x minus V1x. Rho into q, mass density is known here. Mass density you can find out, and q is a discharge you can find out. Mass density standard value, and you can also find out discharge. What is the quantity of water which is flowing through the pipe per second. Then V2 cos theta. So rho q into V2 cos theta, because it is acting in the same direction, minus V1 here. So this is mass density into q, V2 cos theta minus V1. Simple equation. It is very easy for you to write, provided you follow the dimension, the signs correctly and the resolving the force into x and y direction appropriately. Then Fy, the force in the y direction. So we have this is Fy. We can write Fy. Suppose if you see here, there is no force in the vertical direction. When the force is acting in the horizontal direction, you cannot resolve this in the vertical direction. So P1A1 in the vertical direction is 0. V1 in the vertical direction is 0. This is very, very important. Suppose they are giving some angle for P1A1 and also V1. So P1A1 in the vertical direction is 0 and V1 in the vertical direction is also 0. That is very important. So now we have Fy here. And the other force P2A2 here, because it is acting at an angle theta, the P2A2 is acting at an angle theta, so we can have in addition to the horizontal force, also vector force here. So this is P2A2 sin theta. But if you see here, this is acting downwards. This is acting downwards. So P1A1 is 0. Fy, if you, the sign convention you are taking as positive sign in the upward direction. So Fy. So Fy minus P2A2 sin theta. Fy minus P2A2 sin theta, and also we have weight here. Weight is always acting downwards. Weight is acting downwards. So Fy minus W minus P2A2 sin theta. See here, Fy P2A2 sin theta. This is theta minus W here. So it is equal to again mass density into discharge rho into Q and V2x minus V1x. I mean V2y minus V1y, because we are considering in the force in the y direction. So rho Q V2y minus V1y. So then what is V2y? So V2y is V2 sin theta. In the vertical direction we have V2 sin theta. There is no velocity in the vertical direction here. So rho Q into V2 sin theta minus 0. So rho Q into V2 sin theta, this is theta minus 0. So now we have all the values are known except Fx and Fy. Fx and Fy are not known. So find out Fx here and Fy here, and resultant force F is equal to square root of Fx square plus Fy square, square root of Fx square plus Fy square. So this is also important, and we have a number of very good questions in this chapter. So the application of Bernoulli's equation, application of continuity equation and momentum equation clubbed together will have we can expect very good number of problems in GATE examination. Nothing difficult. Only thing you need to remember the equations and appropriate discussion and concepts. And we will move on to the application of Bernoulli's equations also. So we will try to cover the exact theoretical background. The applications, Bernoulli's equation, momentum equation we have discussed, and also applications. We'll try to complete that, and we'll have objective questions and the relevant problems. We'll try to have today or at least tomorrow, so that simultaneously 2 chapters I am covering the theoretical aspects. You prepare well in the complete theory and come back tomorrow with information, knowledge, so that it will be easy for us to understand the objective type of questions. So this is application of Bernoulli's equation. Very, very important once again for object type questions. Another chapter we are taking. So the Bernoulli's equation, as you know, there are 2 important equations. One is Bernoulli's equation. The other one is continuity equation. So Bernoulli's equation, continuity equation. If you take the combination of Bernoulli's and continuity equation, that becomes a tool for to solve many fluid problems. Take Bernoulli's equation, continuity equation, and which will be a tool for many fluid problems. The first one is venture meter. Venture meter. So venture meter is a device which is used for measuring the rate of fluid flow through pipe. Important object type question. What is the purpose of venture meter? Venture meter is a device which is used for measuring the rate of flow through pipe. So this gives a discharge meter cube per second. This gives discharge meter cube per second. Which is used for measuring the rate of flow of fluid through a pipe. Rate of flow of fluid through a pipe. రింగ్ అయితే ఎవరో చూసి నువ్వు అక్కడి నుంచి చెప్తాం. ఇక్కడ రింగ్ అయితే రింగ్ ఇంపార్టెంట్ కదా. రింగ్ అయితే ఎవరో చూసి వాళ్ళకి ఇలా క్లాస్ అని చెప్తాం. అక్కడే ఉన్నాయి. ఇక్కడి నుంచి అయింది, అక్కడి నుంచి చూడలేదు. సో ది వెంచర్ మీటర్ is a device used for finding out the discharge through a pipe. Simple principle here. Simple principle involved here. So this is a venture meter. So we have a inlet section here. Inlet means the water is entering through the pipe. So D1 is the diameter of the inlet section. Inlet is the water which is entering through the pipe. And if you see here, this is converging. The area is, the diameter is, if you see here, the diameter is reducing. In other words, the area is reducing. So this is called convergent cone. Convergent cone. And the center portion is throat here. This is throat. And again it is diverging. So diverging to equal diameter. Diverging to the equal diameter. So this is so this is diverging section here. Diverging section here. So this is inlet, convergent cone, throat and divergent section. So the concept here is the cross section area is reducing here, and this is throat here, this is divergent section, and this is outlet. Inlet, convergent cone, throat, divergent section and outlet. The principle involved here is by reducing the cross section area, what happens? So when you reduce the cross section area, what happens to velocity? Let us say the velocity here is V1 and the velocity here is A2 and the area here is A1 and the area here is A2. When cross section area A1 is more than A2, in other words, we are reducing the cross section area, what happens to velocity? So when area is reducing, the water comes out here in the form of jet here, so the velocity V2 will be more than V1. See the content equation, we have A1 V1 is equal to A2 V2. So in A1 V1 is equal to A2 V2, as A2 is more than A1, V2 should be less than V1, otherwise they cannot equate in the content equation. The same flow, the flow is not changing here. So the velocity at section 2 will be more than velocity at section 1 as the area is reduced here. Then what happens to pressure? Let us say the pressure here is P1 and the pressure here is P2. Take Bernoulli's equation, and as it is horizontal, as the venture meter is horizontal, Z1 is equal to Z2, datum heads are same. As the pipe is horizontal, venture meter, from here to here, this is called venture meter. From here to here, this is called venture meter. So as V1 is more than V2, what should be the pressure here? I mean, as V2 is more than V1, as V2 is more than V1, what should be the pressure here? So to balance the equation, we have Bernoulli's equation P1 by W plus V1 square by 2Z, Z1 and Z2 are equal and can cancel that, and which is equal to P2 by W plus V2 square by 2Z. As V2 is more than V1, so the P1, as V2 is more than V1, so the P1 should be more than P2 to balance Bernoulli's equation. to satisfy Bernoulli's equation. In other words, the cross-section area A1 is more than A2, the velocity V1 is less than V2, and the pressure P1 is more than P2. So that is the concept here. So now for finding out the pressure difference, go back to our pressure chapter. So you can find out the pressure difference between points 1 and 2 with the help of manometer here. With the help of the manometer, differential manometer, you can find out the pressure difference between P1 and P2. So the principle involved here is by reducing the cross-section area, a pressure difference is created. Which enables the determination of discharge. Simple principle here, we are reducing the cross-section area and the pressure difference is created. You can measure the pressure difference and based on that you can find out the discharge. Then another important question in gate is, what is the included angle of convergent cone? So the included angle of convergent cone is around 21 degrees, 21 plus or minus 1. So the included angle of convergent cone is 21 plus or minus 1. The included angle of divergent cone is between 5 to 15. So divergent cone, so that means from here to here. So this is a divergent cone. As the area is diverging, as the area is converging, you can say this is a convergent cone. The included angle here is 21 degrees plus or minus 1. The included angle here is 5 to 15 degrees. Convergent cone. So then if you see here, so why the included angle is more here, why it is less here? One objective question will come after the discussion. So he has asked you, the angle of divergent cone is less than the angle of convergent cone. He has given some ABCD answer which is correct. Obviously the angle of divergent cone is less than angle of convergent cone. What is the reason? Why this angle should be more compared to this one? The reason here is from here to here, as the velocity is reduced here. So this part we are only taking for pressure measurement. This part we are taking only for pressure measurement. So when you reduce the cross-section area, pressure difference is created. And again, there will be acceleration here. Acceleration means the velocity includes here. When you go from here to here, let us say here the velocity is V3. So when you go from here to here, there will be deceleration. In other words, the velocity is reduced. When you give a small distance, suppose if you give a more angle, you will have a small length. So from here to here, this is the length of convergent cone. And from here to here, this is the length of divergent cone. So length of divergent cone is always more than length of convergent cone. And suppose if you give a length of convergent cone less, like length of divergent cone, length of convergent cone, divergent cone less as length of convergent cone, then there will be formation of eddies here, there are huge losses here. So the deceleration obviously with some distance. Deceleration means reduction in velocity, acceleration, deceleration. Acceleration means increase energy, deceleration means decrease energy. So the deceleration a small length, what happens here? There is a separation of flow here, there is a backflow here, eddies are formed. So obviously deceleration, it will be given much distance so that we can avoid separation, we can avoid eddies also. For example, if you give a small distance, then what happens? So the flow will be separated. There is a separation of the flow which causes eddies and huge energy loss and consequent energy loss. So if it is in a small distance, there is a formation of eddies, a backflow. This is the forward flow. You can expect a backflow because of this sudden reaction. So as we are giving more distance, divergent cone angle is less, there will be deceleration slowly and the losses can be minimized if you have a more divergent length. That is one issue. The other issue is the pressure at point 1 and this is the pressure at point 2. If you reduce the cross-section area this value. So suppose if normally D1 or D2 is equal to 0.5 times D1. For example, if it is D1, it is D2. D2 is equal to 0.5 times D1. Suppose if you reduce the diameter to a lower value here, no doubt there will be acceleration. Suppose if you reduce the diameter to a lower value, and that value you can have a pressure here. When the pressure corresponds to D2, if it is less than vapor pressure, what happens? Suppose if you reduce D2 to such a value, at that point the pressure is less than vapor pressure. As you know, vapor pressure is pressure created by vapor due to accumulation of vapor bubble when the top of the container is closed. We have discussed that in the first chapter. So when the pressure at 2 is less than pressure at vapor pressure, what happens? There will be vaporization, which results in cavitation. So important objective type questions. Number of times asking about cavitation. Cavitation is a formation of vapor and air pockets. It happens when the pressure point is less than vapor pressure. And ill effects are the metallic surfaces will be damaged, and there will be corrosion. Metallic surfaces, whatever the surface we have here, that will be damaged if the pressure here is less than vapor pressure. And it is called cavitation. So cavitation means the ill effects of cavitation or the metallic surface is damaged and the efficiency will be reduced. To avoid cavitation, the rule is the diameter at 2, preferably half of the diameter D1, D2 is equal to 0.5 times D1, or D2 is equal to 1/3, 1/3 to 3/4 of pipe diameter. It should be between, D2 should be between D1/3 to 3D1/4. You remember that these are all very important for object type. Then how this is required for finding out the quantity of water flowing through the pipe. Then we have the Bernoulli's equation, continuity equation. So we can use the continuity equation. We can use a continuity equation. Continuity equation is A1 V1 is equal to A2 V2. We can use continuity equation, which is A1 V1 is equal to A2 V2. So based on that, we can find out V1 and V2. We can find out V1 V2 from the continuity equation. Then the next equation is Bernoulli's equation. Bernoulli's equation. So Bernoulli's equation, as you know, you can apply Bernoulli's equation here and here. So P1 by W plus V1 square by 2Z plus Z1 is equal to P2 by W plus V2 square by 2Z plus Z2. Velocities V1 and V2 are known, and we can find out the pressure difference with the help of E2 manometer, and the datum heads are known here. Datum heads Z1, Z2 are known here. So because these two are the same level, Z1 is equal to Z2, and the velocities you can obtain, V1, V2 velocities can be obtained, and the pressure difference can be measured with the help of manometer here. So when it is a horizontal instrumeter, the pressure difference H, which is equal to x into S to S1 minus 1. So this we have done discussion earlier. So H is equal to x into S to S1 minus 1. So as it is horizontal one, so P1 by W minus P2 by W, the pressure difference between 2 points with the help of E2 manometer. E2 manometer you can have the value here. S2 is the specific gravity of manometer liquid. S1 the specific gravity of the water oil which is flowing through the pipe. So you can find out H is equal to x into S to S1 minus 1. So the value of H is known, which is equal to pressure difference. This is x is the mercury displacement in the manometer. This we have studied in E2 manometer. X is mercury displacement, S2 is specific gravity of mercury, S1 is specific gravity of water. So H is equal to x into S to S1 minus 1. So which is equal to P1 by W minus P2 by W. So I can find out the value of H here, and you can also find when Z1 is not equal to Z2, so that means now the ventimeter is not horizontal. So the ventimeter is inclined, the ventimeter is vertical. The only difference here is Z1 is not equal to Z2. Everything is same. The datum head at 1 when it is vertical, when it is not horizontal. When it is horizontal, exponent is Z1 is equal to Z2. When it is vertical, Z1 is not equal to Z2. Then you need to consider Z1, Z2 also. So here the pressure difference is only P1 by W minus P2 by W. Now it is P1 by W plus Z1. So P1 by W plus Z1 is piezometric head. P1 by W plus Z1 is piezometric head at point 1, and P2 by W plus Z2 pressure head and datum head is piezometric head. We have discussed that. So piezometric head at 1 minus piezometric head at 2 is equal to same equation, but now it is inclined ventimeter. You need to consider Z1, Z2. Z1 and Z2, everything is same. In that case, it is also equal to H is equal to X into S to base 1 minus 1. So I can find out H appropriately with the help of E2 manometer. And now the quotient of discharge. So the quotient of discharge is actual discharge by theoretical discharge. The quotient of discharge is actual discharge by theoretical discharge. Actual discharge is the quantity of water which is actually supplied per second. Actual discharge is the quantity of water which is collected at the end. So theoretical discharge is the quantity of water which is supplied and this is available. For example, you take here the quantity of water which is supplied is theoretical discharge. The quantity of water which is available here, that is actual discharge. Theoretical discharge is the quantity of the water which is allowed, which is supplied to the pipe, and the actual discharge is the quantity of water which is available from here and the exit. So the CD quotient of discharge is actual discharge by theoretical discharge, and because we have made gradual convergent and divergent, so the theoretical discharge is the quotient of discharge is 0.98 and should not be more than 1. The quotient of discharge, some of the students they are giving more than 1. So obviously there are some losses when the flow is from one end to other end. So because of those losses, here the losses are less per venture-meter, the value of CD is 0.98. As the losses are less per venture-meter, the quotient of discharge is 0.98, very close to 1. If the calculations are wrong, you may get the value of CD more than 1, which is not correct. Obviously, the actual discharge should not be more than theoretical discharge. The water which is available will not be more than the water which is supplied. So CD is equal to 0.98. So then the discharge Q actual is equal to CD into Q theoretical. So this is CD, Q theoretical, A1, A2. What is A1? A1 is the cross-section area at the inlet. A1 is the cross-section area at the inlet, and A2 the cross-section area at the throat. So this is A1 and this is A2 here. Cross-section area at the throat is A2 and this is A1. And the square root 2GH, A1 square minus A2 square, the area A1, A2, and square root 2GH, G is 9.81 and H is 1 by 2 and this H is H. Both are same. So this H both are same. This you can substitute here so that you can find out discharge. The purpose of intermediate is to find out discharge. You try to remember this equation CD A1 A2 square root of 2GH all by square root of A1 square minus A2 square. Simple equation, but try to remember this equation is very, very important, and H is equal to X into S to base 1 minus 1. The other one is, other application is R Orifice meter and ventimeter both for finding out the pressure, finding out the discharge of water which is flowing through the pipe per second. So only orifice meter is it requires less space and also cheaper So this is orifice meter. Orifice meter, it is a flat flat circular plate with a opening here, flat circular plate with a opening here. And if you see here, earlier ventimeter, there is a gradual convergence and again divergence. And the water, this is the water flow here, water flow is suddenly reduced here. A circular plate obstruction with an opening, the area is suddenly reduced. So the area is suddenly reduced here. And as it is reduced suddenly here, it requires less space, only plate requires very less space. The principle involved is also same. So by reducing the cross-section area, so this is the area here, we have considered this is the area of the flow, and this area of the flow is reduced to this value. So here D1 here and D2 here, and the area is pi by 4 D1 square and pi by 4 D2 square here. So the cross-section area A1 is more than A2, and what happens to velocity? Velocity at point 2, velocity at 2, V2 is more than V1. And the same discussion for ventimeter, and the pressure here P1 is more than P2. So once again, the principle involved here is by reducing the cross-section area, pressure difference is created, and by measuring the pressure difference with the help of manometer, we can find out the discharge. Same principle. And in the orifice meter, we have a important point to note. So when water is reduced here, the flow area is reducing and again increasing here. So this is the jet here. The jet area is reducing and then increasing here. And this is the section, this is the point at which the jet has minimum cross-section area. This location, normally at a distance of d by 2, this is if it is d here, the opening is d here, it happens at a distance of 1 by 2 of d. So if d is the diameter of the orifice is opening here, and this should be normally half of the diameter here, d by 2. Then the jet area has reduced here and again increases here. And you can say this is a point called vena contracta. This is a point called vena contracta, where the jet has smallest cross-section area. So this is the jet here. The vena contracta is the point at which the jet has minimum cross-section. Important object type or gauge. What is vena contracta? ABCD we have. Vena contracta is the point at which jet has minimum cross-section area. For the ventimeter, you need to know cavitation. Important object type. Same principle here. The equations are same. So discharge is also same, which is equal to CD A1 A2 square root of 2GH A1 square minus A2 square root. The quotient of discharge is actual by Q theoretical. When it is horizontal position, Z1 is equal to Z2. Z1 is equal to Z2. An inclined orifice meter. So when Z1 is equal to Z2, so this H is a small h, Venturi head, it is also called Venturi head. This is the same value, h is equal to x into st plus 1 minus 1 is equal to p1 by w minus pt by w. When z1 is equal to z2 for horizontal position, that means the atom heads are same. When it is inclined, so when the orifice meter is connected for a vertical pipe or inclined pipe, so this is a piezometry head for point 1. which is pressure head plus radium head at point 1, pressure head plus radium head at point 2, piezometric head at point 1 minus piezometric head at point 2, which is also equal to H is equal to X into ST plus 1 minus 1. And you can substitute the values here. Q is equal to CD. Coefficient discharge is very less here, 0.6 to 0.7. So we have more losses here. When the losses are more, the actual discharge is much less than theoretical discharge. So in centimeter, the losses are less. That's why the coefficient discharge is 0.98. Whereas here coefficient discharge is 0.6 to 0.7. So the losses are more here, and it is cheaper arrangement, and it requires less space. So the value of CD varies from 0.6 to 0.7, whereas 0.95 to 0.98 for 1 centimeter, and A1 is the cross section area, and A2 is the cross section area at 0.1, cross section area at 0.2, and H is the mercury head here, and this is the mercury displacement, and this is pressure to mercury, pressure to water minus 1. And A1 square minus A2 square square root. A1 is the area at section 1 and A2 is the area at section 2. So this is also important. 1 centimeter or 5 centimeter applications of Bernoulli's equation is asking frequently. We take petard tube. What is petard tube? So earlier cases, both 1 centimeter and R5 centimeter, we have used it for finding out the quantity of water which is flowing through the pipe or discharge. 1 centimeter and R5 centimeter for finding out the discharge, whereas petard tube is for finding out the velocity. Very important object type, match the 1 centimeter R5 petard tube and discharge, velocity, etc. Please have a memory, very important. The petard tube is used for finding out the velocity. Then what is the principle here? So this is the petard tube here. This is the petard tube bent at right angles. Suppose if you see here, this is 90 degrees here, this is 90. Petard tube. Petard tube used to find out the velocity of the water which is flowing through the pipe. So one end is exposed to this point here, the other end is open in the atmosphere. If you see here, petard tube is a bent tube made at right angles, and one end is open in the atmosphere, one end is open in the atmosphere, the other end is exposed to water here. The principle involved here is, by reducing the velocity to 0, so here we have some velocity here, V1 is the velocity of the water, and it is required to reduce the velocity at 0.2 to 0. When the velocity is reduced, no doubt the pressure, there is a rise of water here. So by reducing the velocity at a particular point, the principle involved here is, the velocity of the flow at a particular point is reduced to 0, which is known as stagnation point. What is meant by stagnation point? Water stagnates. Stagnation point is the point at which velocity is 0. Stagnation point is the point at which velocity is 0. So as we have reduced the velocity to 0, so this point is called stagnation point. This point is called stagnation point. So now what happens here? The water is coming with velocity V1. So by reducing the velocity to 0, and as we are reducing the velocity 0, and this will measure, because of this will have an increase in pressure. So increase in pressure can be measured with the help of a petard tube, and which is a basis for finding out the velocity. The principle involved here is the velocity of the flow at a particular point is reduced to 0, which is known as stagnation point. So by measuring the pressure energy at this point, the velocity of the flow is obtained. Because of reduction in velocity, there is a pressure change. So measuring the pressure energy, that enables us for finding out the velocity. And what happens here? So the fluid here at point 1, you have velocity here, and it approaches the point 2. When the velocity what approaches here, so this flows around the tube as it is a stagnation point. This flows around the tube, consequently there is a pressure rise here. Then we have three aspects here. So this is a static head. So because this value capital H is called static head, and this H is called dynamic head. So this H is called dynamic head. The small h for dynamic head and capital H for static head. Capital H for static head. So if you see here, this is all static here, and because of this velocity change, there is a rise here above surface, and this is called dynamic head. Why I am stressing this is in the object type questions is confusing with static head, dynamic head, stagnation head, total head. The other one is stagnation pressure head. So because of the stagnation, the total head, this is the dynamic head, changes dynamically, depends on the velocity here. This is the static head, constant. So the stagnation pressure head is equal to capital H plus H. So capital H plus H is the stagnation pressure head or total head. Sometimes you can call it the total head also. So total head is equal to the static pressure head and dynamic pressure head, or the total head stagnation head is equal to static head plus dynamic head. So this petard tube which measures the total head or stagnation pressure head. It gives H plus H. You can have a scale here, so you can find out H plus H. Then how will you get this velocity? Simply apply Bernoulli's equation. Based on that, you can find out the velocity. Or you can remember that the datum heads Z1 is equal to Z2. Or you can take that the Bernoulli's equation here, P1 by W plus V1 known, V is not known, and Z1 and Z2 are equal, so you can take Z1 is equal to 0, and P2 by W, so P2 by W is equal to H plus H, capital H plus small h, H plus H. So the pressure is equal to H plus H, and V2 is the stagnation point, V2 is the value 0 here, and Z2 is 0. So the final equation is H naught, H here, H plus velocity is not known, V square by 2G, and Z1 is equal to Z2 0, and P2 is equal to H naught plus H plus H, and velocity 0, Z2 0. So finally the velocity is equal to square root of 2GH. The velocity is equal to square root of 2GH, where H is dynamic head, not static head. H is dynamic head. So stagnation point, static pressure head, dynamic pressure head, stagnation pressure head. The actual velocity is equal to square root 2GH. And what is this C? This C is called petard tube constant. This C is called petard tube constant. Maybe 0.6 to 0.7 normal. So again, actual velocity or petard tube constant C is equal to V actual by V theoretical. V actual by V theoretical. We have obtained the theoretical velocity square root 2GH now. So theoretical velocity is square root 2GH, and actual velocity is equal to petard tube constant multiplied by square root 2GH. Square root 2GH. What is H here? H is again simple. So H is venturi head. H is venturi head. This H and this H both are same. So H is equal to x into S2 by S1 minus 1. So this is x is the mercury displacement, S2 is the specific gravity of mercury, and S1 is specific gravity of fluid minus 1. So you can also use Vincent meter. I mean, you can also use the pressure measuring instrument for finding out directly the value of x here. So you can find out h, which is equal to x into. We can find out the value h, which is equal to x into s to base 1 minus 1. So directly you can measure the dynamic pressure head h, and sometimes you can also use manometer, YouTube manometer, and so that you can find out mercury displacement again, and x is the mercury displacement, s2 is specific gravity of mercury, and s1 is specific gravity of water. So h is equal to x into s2 by s1 minus 1, and you can substitute the value here. So V actual is equal to c into square root 2gh. So c is the Petard tube constant, and h is equal to x into s2 by s1 minus 1. So this is the theoretical background completely for dynamics chapter. So fluid dynamics is the forces, the Penrose's equation, very very important, the momentum equation, steady flow momentum equations, and the application part pipe bend, and we have also discussed the applications of Penrose's equation, Vincent meter, orifice meter, and Petard tube. This is very very important for this is almost a key. So like fluid properties, fluid kinematics, and pressure chapter and hydrostatic forces. This is very very important for dynamic point of view. So fluid dynamics, which includes which covers applications also, almost 2 chapters. I have considered the complete theoretical discussion. So based on that, we have problems and gate questions, etc. We'll be dealing tomorrow. But it will be easy for you tomorrow only, provided if you study these 2 chapters discussion tomorrow by today, so that it will be easy for you tomorrow. Again, thank you very much, student friends. Tomorrow we'll meet at 10:30, and we'll be taking up the problems on application of Bernoulli's equation, and also the gate problems, solutions, and discussion. If time permits, we also start analysis of pipe flow, other chapter, other important chapter.